Hello there, Mr. Sutton, bringing you the AB Calculus 412 Extra Practice number 2 solutions on motion. For this problem, we have a particle moving along the y-axis so that its position is given by this y of t function, which statement describes the motion at time 1. So if you look at these statements, they're all talking about whether we're moving down or up, and also whether we have decreasing or increasing velocity. So to answer the question of down versus up, we need to know the sign of y prime. To answer the question of decreasing versus increasing velocity, that's talking about y double prime, the change in velocity. All right, so let's start with y prime. We're going to need to know that one. So first derivative is going to be 3t squared minus 8t plus 4. And we want to figure out what y prime, which is really just velocity, is doing at time 1. So plugging 1 into all of this, we're going to end up with, let's see here, we've got 3 minus 8 is negative 5, plus 4 is negative 1. So we end up with negative 1. Now this is a negative number, and since the motion is along the y-axis, a negative number means we are moving down. All right, so to figure out if our velocity is increasing or decreasing, we next need to look at the rate of change of velocity, which is going to be y double prime. So that's going to be 6t minus 8. And now if we plug 1 into y double prime, that comes out to 6 minus 8, which is negative 2. Since that is negative, that tells us that the velocity is decreasing at time 1. So that's going to be, let's see here, we're moving down, decreasing velocity. That's choice A. For this problem, we have a particle moving on the x-axis whose position is given by this graph above. We want to know which of the following best estimates our speed at time 8. All right, well, if you've already got position, then to talk about velocity, which is going to be speed in this case because we're moving in just one direction, you just need to find the average rate of change to estimate it. So average rate of change of x, we'll say from 6 to 10 because that involves 8, which is the time we want the estimate at. Average rate of change from 6 to 10, that's going to be x of 10 minus x of 6 over 10 minus 6. So that's going to be 30 minus 30 over 10 minus 6. Well, that's just 0 over 4, which comes out to 0. And that kind of makes sense because, I mean, if you really understand what's going on here, this x of t, this is telling you how far to the right you've moved at every given time. You know, at time 6, you're at 30, whatever units these are, we'll say feet, whatever. And then at time 10, you're still there. You have an average speed of 0 at that point. So that's going to be choice A. For this problem, we have a rocket leaving the surface of the Earth, traveling straight up. The height in feet, which we're calling y of t, and the time in seconds, which we're calling t, values of those between 0 and 600 are given in this table. We want to know, based off the table, when is the speed of the rocket most likely the greatest. So one thing to get straight real quick is that speed and velocity, which are different, are actually going to be the same on this particular problem, just because our rocket's traveling straight up. So when they're asking when the speed is the greatest, they're asking when the velocity is the greatest on this particular problem. Next, we don't really have anything to go on in terms of specific velocities or speeds other than our positions here in this table. So what we're going to do is just find the average speed or average velocity at various times, and that's going to be what we base our answer off of. So for example, at time 100, I don't know the velocity at time 100, but I can find the average rate of change of position of y of t on an interval that 100 falls on. So I'm going to find average rate of change on the interval from 0 to 200 seconds. So let me see here. I've got the y values. That's going to be 400 minus 0 over the x values, 200 minus 0. And this is a calculator problem, but I'm just going to do this one in my head. 400 over 200 gives me 2 feet per second. Okay. Well, let's estimate some other ones. For 200, that's between 100 and 300. So I'm going to do 1360 minus 50 over 300 minus 100. And let me do that on the calculator. So here I am plugging this in on the calculator. Now, normally I would use a fancy fraction, alpha y equals, in order to make a fraction and plug it in the nice formatting. The reason I'm using these parentheses with the division symbol around this is so I can get a decimal without having to explicitly convert it to a decimal. If I use fancy fraction formatting, I get a fraction back usually, and it'd be easier to compare these if I have them as decimals. So pressing enter, that's about 6.55 feet per second. And now to estimate time 300 speed, that'll be 3200 minus 400 over 400 time 400 minus time 200. And what's this going to... I probably don't need a calculator. This is going to be 2,800 divided by 200, which is going to be 14 feet per second. And then what else do we have? So these speeds appear to be increasing. Let's see if that continues now. Doing this last one, estimating at time 400, that's 6,250 minus 1360 over 500 minus 300. And let's plug this in the calculator now. So putting that in there, again, being careful to use parentheses around the stuff in the numerator and the denominator, that comes out to 24.45 feet per second. So definitely, based on the data anyway in the table, the time at which we probably have the greatest speed is going to be time 400, choice D. For this problem, the position of a particle moving to the right on the x-axis is given by x of t. And let's see, that's between 0 and 100, and x of t is a linear function. We want to know which of the following gives the best estimate of speed at time 20 minutes. So because we have a particle that is moving to the right, we're told that it's moving to the right, so it's not changing direction. That means that speed, since we're moving in one direction, speed and velocity are going to be the same thing on this problem. And velocity in general is the instantaneous slope of position of x of t. Now, since x of t is a linear function, that means that the slope is going to be constant. So we just have to find the slope of the x of t function, and that will tell us the velocity, which is the speed on this problem. So looking at our answer choices, choice D says the slope of the graph of x of t. So that's definitely what we're looking for here. Now, just to take a look at some of the other answer choices, x of 20, well, that was your position at time 20, so that doesn't tell you the speed. X of 20 over 20, well, that would be your average rate of change in position, which would be velocity if you were starting at 0, time 0, which is all well and good, but it doesn't necessarily tell you a whole lot about the speed at time 20. So the actual slope of the graph at time 20 is still going to be a better answer than the average slope between 0 and 20. And then this last one, C, x of 21 minus x of 19, this is just the change in position from time 19 to 21. That's not going to tell you the speed by itself. So choice D. For this calculator-based problem, we have a mass of a colony of bacteria modeled by this P function, and we want to know what the instantaneous rate of change of this mass is at the moment the colony reaches a mass of 6 grams. All right, well, we're asking for two things really embedded in this problem. We want instantaneous rate of change of the mass, which is going to be P prime, but we need a time to plug into P prime. And that time is going to be the time at which the colony, which is represented by P of t, reaches a mass of 6 grams. So strategically, we need to figure out what time satisfies the equation P of t equals 6, at what time P of t equals 6, and then we'll plug that into P prime. So this is a calculator problem, and I'm going to have to use the calculator to solve this piece. So here I am in the y equals. I've entered my function, which was 2 plus 5 inverse tan of t over 2, in my y1 here, only I'm using x over 2, because that's the input variable on the calculator. I want to know when this thing equals 6, so let me just plug in 6 to y2, and now I'm just going to see where these things intersect. Now, I have no idea what window to use on this, and it doesn't look like I'm really getting a whole lot of guidance from anything in this problem. So I'm just going to use a window, a standard window, it's 10 in every direction, zoom 6, and hope for the best. And if I don't see where they intersect based off of this, well, then I'll just move my window further out. So there's the bacteria. There is the horizontal line 6, so I do see pretty clearly where these are crossing. So let me do second trace and then option 5 for intersect. Let's just move a little closer to that intersection, press enter 1, 2, 3 times. It comes out to about 2.0593. And I'm going to store that as a variable like a on my calculator, just so I can turn around and use it fairly quickly. So let me quit out of here, and I'm going to press the store button and then alpha a, and now I've stored that magic time as a, so I can use it whenever I want by just doing alpha a and pressing a. Cool. What do I have to do with this time? Well, I wanted to know the instantaneous rate of change of the mass of the colony. So I need to plug this value into p prime. All right, so we have p prime of a, and I don't actually need to figure out what this derivative looks like algebraically. For one thing, it's multiple choice, but even if this were a free response, I could just say p prime of a, because you are allowed to take the derivative at a single point without actually showing algebraically what it looks like. So on my calculator, I'm just going to go to Math, option 8 for derivative. I've got dx. In here, I'm going to put, let's see, alpha trace y1. That's where I stored my p function. And then I'm going to do this at x equals, well, now we need the time a that we just found. So I'm going to do alpha a and press enter to get about 1.214. And let's see here, that's going to be in grams per day. So that gives us answer choice C. For this problem, we have oil spilled onto a kitchen floor. Oh no. The area covered by the oil is given by this A function, measured in square centimeters, and then time is in seconds. We want to know which of these expressions tells us the rate at which the area covered by the oil is changing at time 10. So looking through each of these, A of 10, well, that tells us how much area is covered by the oil. So this is the area at 10 seconds, not what we're looking for. We wanted the rate of change of the area. A of 11 minus A of 9, that's the change in area from time 9 to time 11. So again, not really what we're looking for. A of 10 over 10, well, if we have 0 oil on the floor at time 0, this would give us the average rate of change of the oil from time 0 to 10. But again, that's not going to be telling us the exact rate of change of the oil at time 10. To get that, we need A prime of 10. That's the instantaneous rate of change at time 10. So choice D. For this one, we have a particle moving along the y-axis. The graph of its velocity is shown above, and we want to know how many times our particle changes directions between 0 and 4.5. So if I'm asking where the particle changes directions, I'm looking for sign changes in velocity. So the velocity is going to change sign according to this graph. This is going to be whenever it crosses the x-axis. So this happens 1, 2, 3 times, and we have a bounce here. This doesn't count. This origin intersection also does not count since we don't know if we're crossing or not. So 3 times guaranteed. This means that our particle changes directions 3 times on 0 to 4.5, giving us choice A. For this problem, the acceleration in meters per second of a car is modeled by this A of t function. We want to know the maximum acceleration on the interval from 0 to 6. Since we're asking for an absolute max, we're going to use the candidates test. So we're going to test out the car's acceleration at times 0 and 6 because we always include the endpoints. But we also have to find critical values between 0 and 6 to test as well. So let me do A prime to find those critical values and set that equal to 0. That'll be 3t squared minus, this is now going to be 15t plus 12, and all of that equals 0. So now we can solve this with the quadratic formula or by factoring. I'm going to factor this thing. And before I do that, though, let me take a 3 out of everything. That would leave me with a t squared minus 5t plus 4. So we've got 3 parentheses, t squared minus 5t plus 4 equals 0. Two things that multiply to 4 and add up to negative 5. So we have t minus 1 and t minus 4. And we see that our critical values happen at times 1 and 4. And those are both in seconds. All right, so let me plug my critical values into the original A of t function, starting with 0. So 0 is an easy one. That zeroes out anything with a t, leaving us with just that constant 10. Next, let's plug in the critical value 1. That's also fairly easy to deal with. We do have this fraction here that I'm going to deal with last, but looking at the non-fractions, we have a 1 plus a 12 is 13 plus 10 is 23. So that's going to be, let me see here, 23 is 46 halves minus 15 halves is going to be 31 halves when all is said and done, which is 15.2. So it's actually bigger than the 10 over here if we need to compare them. Let's keep going, though. Now we have to plug in critical value 4. So that's going to be 64 because 4 cubed. And then let's see here. This is going to be 16 times 15 halves. So 16 divided by 2 is 8 times 15 is going to be 120. So we're subtracting 120. And then let's see here. We've got 4 times 12 is 48. We have a plus 10 at the end. And what does all this add up to? Well, let me do the positive numbers first. So we've got 64 plus 48. Let's see, that's 72 plus 40 is 112. Plus 10 is 122. Minus 120 comes out to 2. Now for the last one, this one's going to be the most beastly of all, 6. Plugging that in there, we're going to have 216 minus, and now let's see here, this is 15 over 2 times 36. So 36 divided by 2 is 18. 15 times 18, well, 10 times 18 would be 180. 5 times 18 is 90, so that's going to be 270 altogether, so minus 270. And then we've got 6 times 12, a little bit easier, that's 72, plus that 10 over there. All right, so what's all this add up to? We have 216 and 72 gives me 288, plus another 10 is 298, minus 270 is 28. So out of all of these, we've got 0, we have, or no, we're setting that equal to 0. These are the candidates down here. We've got 10, we've got 15.5, we've got 2, we've got 28. 28's the biggest one. So our max acceleration happens at time 6, and it's going to be an acceleration of 28, and this is going to be meters per second, or meters per second squared. So out of our answer choices, this is going to be choice D. For this free response problem, the number of mosquitoes in a field after a rainfall is given by this M function, where we're modeling time in days, and obviously M of t is a number of mosquitoes. And let's see here, this happens between 0 and 18. All right, so using correct units, this is our first task. Interpret M prime of 15 equals negative 171. All right, so let's see here. We have to have a time and what it means and all the rest of it. So this is saying that at 15 days, because that's our input, 15 days after the rainfall ends, the rate of change of mosquitoes in our field, the number of mosquitoes, is changing at a rate of, let's see, this is negative 171, and that's going to be mosquitoes per days. For this part of the problem, based on the model, we want to know the absolute max number of mosquitoes in the field over this interval. Justify the answer. So on this one, let's go ahead and find some critical values. One option here is using the candidates test, where we plug in critical values and the endpoints into this. But let's see how many critical values there are, and then we'll decide what method to use. So for that, I need to take M prime, which is negative 3t squared plus 24t plus 144, and set it equal to 0 and solve it. So I can start this process by factoring out a negative 3, leaving me with t squared minus 8t, and then this is going to be, let's see here, 144 divided by 3, that's going to be 48. Yep, minus 48. Okay, so now factoring this, things that multiply to negative 48 and add up to negative 8, well, this is a little bit more arithmetic. So let's see here. We've got, 2 and 24 doesn't work. 4 and 12. 4 and 12 could work. How about t plus 4 and t minus 12? There we go. So this is going to equal 0 at time negative 4. And let me write equals 0 there. There we go. Equals 0 at times negative 4 and 12. So those are our critical values. Now, one thing very important in this situation is that this critical value of negative 4 is not on the interval here. So what that means is there's actually only one critical value on this whole interval. Normally, you have to use the candidates test when you're trying to find absolute maxes, but if you only have a single critical value, then whatever kind of extrema it turns out to be is also going to be an absolute version of that extrema. So let's figure out what kind of critical value 12 is. The fastest way to do that is by using the second derivative test and just seeing what the sign of m double prime is when we plug in 12. So second derivative, that's going to be negative 6t plus 24. And if I plug in 12 to this, that's going to be negative 72 plus 24, which is negative 48. Most importantly, that's a negative number. That tells us that there is a local max at time 12. Now, since there's only one critical value, since 12 is the only critical value on this whole interval, that means that it also is the absolute max at time 12. Because if you think about it, the fact that it's the only critical value means that until you get to 12, since it's the local max, you're increasing. And then you're decreasing after time 12. So time 12 must be where your absolute max is on this thing. All right, so they actually wanted to know the maximum number of mosquitoes. So at this point, we have some more painful arithmetic. We have to plug 12 back in to this function, and we wouldn't have had to do this if we had done the candidates test, but it would have been, well, we would have already done this if we had done the candidates test. So now it's one of those pay me now or pay me later situations. We're paying later. So we've got m of 12, and what is this going to come out to? So you're going to have to do this by hand. This was a no calculator problem. Basically, you've got negative 12 cubed, and the funny thing is, though, this is also going to be essentially 12 cubed, 12 times 12 squared, and this last one is also going to be 12 cubed, which is, this is 12 squared times 12. So if you find one of these values, you've actually found all three, which is kind of nice. So let's see what 3 12s multiply to give us. 12 times 12 we know is 144, and 144 times 12, well, let me do 144 times 10 plus 144 times 2. So that's going to be 1,440 plus 288, which comes out to, let's see, that's going to be 1,728. So we've got negative 1728 plus 1728 plus another 1728. Well, these first two conveniently cancel, leaving us with just 1,728 mosquitoes. For this part, we want to know for what t-values the rate of change of the number of mosquitoes in the field is increasing. So basically, we're asking where m prime, which is the rate of change of mosquitoes, where m prime is increasing. Well, that means we need to know where m double prime is positive. So m double prime, recall from part B, was negative 6t plus 24. To figure out where this is positive versus negative, I'm just going to find critical values by setting this equal to 0 and doing a little sign analysis. So if we subtract 24 and divide by 6, we see that our only critical value here is going to be 4. So I'm going to make a little m double prime number line here. We already have endpoints of 0 and 18, and in between there's the critical value 4. So testing a number between 0 and 4 in m double prime, like 1, that's going to be negative 6 plus 24, which is positive. Number bigger than 4, how about 5? That's going to be negative 30 plus 24, which is negative. And we see here, since m double prime is positive from 0 to 4, that means m prime is increasing on the interval from 0 to 4. So the rate of change of mosquitoes, m prime, increasing on 0 days to 4 days. For this last part of the problem, where there's mosquitoes, there's hopefully some bats to eat them, right? The number of bats in our field is modeled by B, where B is a function of the number of mosquitoes. So based on these models, we want an expression for the rate of change of bats at time A. Well, we need to figure out a function for B to begin with. So they said that B is a function of M, so why don't we just write B of M of T? That'll be our number of bats. And now the rate of change of bats at any time, this is going to require the chain rule. We're going to have B prime of M of T times the derivative of M, so times M prime of T. This is our overall rate of change of bats. But now we wanted this at time A, so we're just going to replace all those T's with A's. And we get B b prime of m of a times m prime of a, and we're going to call it a day on this one.